Alrighty, time to get on the grind. Count the number of good subarrays. Given an integer array nums and integer k, return the number of good subarrays. Good is defined as at least k pairs of indices such that they're in order and the values are equal. There are at least k pairs of indices. Subarray is contiguous. Okay, yeah. So here, if you take everything here, then there's 5 pairs within this. Like 5 choose 2 is 10. So that's 10 pairs. Okay. And 2, so you need to have at least 3 elements. Oh, I see. So it doesn't have to necessarily be all the same values. Ooh, this might be a little rough. I was hoping to have everything be the same. Alright, let's go ahead and consider how to do this. So for counting stuff, if you have some number of identical values in your subarray, then it'll be n choose 2 as pairs from that. So if there's 5 identical values, then there'd be 5 choose 2, which is 10. But now you want to do it with possibly other values. So let's say you had like let's say you had x, 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 y, y. So that'd be pairs from x times pairs from y. And that would be like x, the number of x's choose 2 times the number of y choose 2. And that has to be greater than or equal to k. And you can extend that out to all the other duplicate values. Interesting. And then you need to find the number of good subarrays. So subarrays has to be, no, doesn't have to be some contiguous. Could be, no, subarray is contiguous. Something. Okay, so generally this seems like a sliding window where you track the number of identical values within your window. The number of identical values within your window. Is that correct? Because in theory, you'd start by trying everything, right? You'd start by trying the whole subarray. Because you're never going to have smaller numbers in your whole subarray. Try your whole subarray, see how many pairs you have in that. And then what you do from there, you remove elements from the left or right side from the whole subarray. So you count the number of subarrays, or the sum of number of pairs within the whole array. That's 3. Then you would remove elements from the left side until you couldn't remove any more. Or I guess this for the right side. So you remove the 4, you see if this works. You see if 314-322 works. It still works. So you can remove this one. See if that works. That doesn't work. So this is pretty long array. I think you could definitely do this recursively, but the stack would be too long if they have that much recursion. So, you could, I see. It's a minimal sliding window, I guess. So the minimum, so you look at the window where it's at the very minimum of what you need to hit the K, and then you would say that anything outside of that window that extends either to the left or right work as well. So I think, okay, yeah, this is, so I'm going to try a sliding window. This is find the smallest subarray that satisfies the constraint, which is pairs greater than or equal to k, and all subarrays It's gonna double count and stuff. Yeah, okay, I see. So null subarrays pass that to the right will be good as well. So I think the left side needs to be the left side needs to be fixed. Yeah, I think the left side needs to be fixed. So for left in range n, so you'd also have the right side be fixed. I think it's a little, it makes more sense in my head for it to be right side is not fixed. But there's a possibility that you can write it either way. So the answer is that as we track the window, we need to know, as we track the window, we need to know the counts of stuff. Let me think, the counts of stuff. Let's say current count is 0, which is the, I guess you could say pairs. And I guess you need the actual counts of things. Counts is going to be a default dictionary of ints, maybe. The values are between 1 and 10 to the 9th. Value exceeds, so I mean the values are just so large that you really don't want to have like a array to keep track of the frequency, so I think I'm mapping this fine there. So say the value is equal to the nums at this, nums at right. So each time you do it, right, so here I'm going to open the window, extend right side of window until extend right side of window until constraint is reached. Constraint is satisfied. There's at least k pairs. So, okay, so currently the right side is at 0. So I'm going to say while the pairs is less than k, then the value is taken from the right side, and then eventually I'm going to keep on adding to the right side. So the value is taken from the right side. I say the counts of this value is going to be incremented. Then that's going to affect the number of pairs. Okay, so for instance, so the first thing I'd do here would be the right is at index 0, the value is 3. It says that there's now 1, 3 within the window. And then that would affect the number of pairs. Well, not really, but I would need to get the combination. What is the Python combination? Python combination function. I really should memorize this. Is it math.combine? Math.com? Yes, math.combine n.k, n comma k. There's also probably a module with that, right? Or was that with the factorial? No, it was with the modulo. Like, which was it before? Count. There was some recent one that was mod. Alright, I'll have to look at it later on. Just to refresh my memory. Okay. So let's say that the new pair. So the first three is not really going to matter, but let's say it's something that actually creates some combination. It would be, let's say C is equal to math.combination. Well, yeah, that's fine. Math.combination of the counts of this value, choose 2. So that's the number of pairs that this thing now creates. So in theory, that would multiply with the number of ways everything else is done. So if the current pairs is equal to 0, then the pairs is now equal to this. But if the current number of ways that the pairs is, the number of pairs is, if the current number of pairs is not 0, then you would change it, right? You would divide by how many previous pairs there are and multiply by how many, you divide by how many previous pairs were constructed using this. So let's say you had an array that was all ones, right? So, the first time, the first one, there's no pairs created. The second one, there's one pair created from these two. So at that point, the number of pairs is 1. And then the third one, that would cause it to have 3 ones, which is 3 choose 2, which is 3. But you want to say that, well, I guess that doesn't really showcase it. Let's say it's 2, 2, 1, 1. So the first two doesn't make anything. The second two makes the pair. The first one doesn't really make anything. There's no new pairs there. Actually, let's see. If C equals 0, then continue. I need to change the right side first. Okay. If it doesn't make any pairs from this combination, then it doesn't change anything. But anyway, so you have 2, 2, there's a pair there. There's a 1, 1, there's another pair there. And the total number of pairs would be the sum of those two. Is it the sum or the product? This should be the sum. There's one pair is created from here, there's one pair from the other destruct. Okay. So if C equals, if the number, yeah. But if the number is not 0, so you can create a pair here, then you need to add how many pairs you create and subtract by how many pairs you removed or you previously created. So for instance, if you create, so if you had one pair and you look at the third one, there's now 3 pairs you can make from the, maybe you can just say this. Maybe you can say that, really. So the number of new combinations, the new pairs, would be how many you could create using the current count minus how many that you already previously counted. Yeah, that seems fine. In that case, maybe you don't need this if statement. You can just say pairs plus equals this value. If this value is like 1 choose 2 minus 0 choose 2, that'd be 0. So it doesn't really change it. Okay, I think that's fine. Okay, so it does that. So then it basically extends it all the way to the right side until you get to a point where, okay, so I think it does need to stop at while right is not outside of the bounds. Okay, so while this is true, it keeps on doing that, and then it says if pairs is greater than or equal to k, then increment the answer by 1. Increment the answer by the number of subarrays where this right side is at least this far. So for instance, imagine there's like 5 ones here and a bunch of other numbers after it, like 10 other numbers after it. The 5 ones here, that right bound of this spot would be, could be extended all the way to the end of the array. And all those would be good subarrays. The left side is fixed at 0. So the answer is include all subarrays to the end where right goes to end of array. So here the right would be at 5. So it goes, yeah, at this point right is 5. So 5 would be n minus right plus 1, I think. 5 minus 5 plus 1. And then, okay, at that point, you're done with that window. And now, now adjust left side of window. Basically remove left element from consideration. So we'll say that that value is nums at left, and we need to just remove the combinations of that. So counts of this value is decremented by 1. Yeah, so it'll be the number of combinations that you remove by removing it would be the difference between the number of previous combinations of that value. Choose 2 minus the number of new combinations of the current number of combinations. So that's the difference between, that's the drop off. So then pairs minus equals that value. And I think that's correct. Counts of the value. The value is nums at left. Huh, interesting. What is going on here? Oh, wait, there's two things. There's counts and count. Guess maybe count is actually a function. Okay. Fast it, but definitely not fast. Let's consider how this thing is going slowly. I guess I'm making a lot of combination calls. Yeah, let's see. Making a lot of combination calls. I wonder if it would work faster if I cached it. Let's say find combinations of n, choose n, c, yeah, and choose r. Return combination of n, r. Alright, so let's go. Let's do find com this. Find com this. Find combination this. Alright. So this one is less memory intensive. It's the same memory. Okay, so caching it didn't really do very much. Let's think about this. So you extend out the right side. So while right is okay. Go to the right side. Hmm. 279, there's something that's like 37 milliseconds. Pretty sure this is, don't think you can just work off of the frequencies. Can you work off just the frequencies? No, I don't think you can. Because like if the ones here were all grouped up, like let's say the array was ones and then a bunch of twos afterwards, or like 2, 3, 5 afterwards. If the ones were all grouped up, then that means that your subarray, your good subarrays are all the ones and then the 2, the 3, and the 5. But if you had something where the 2, 3, 5 were interspersed within it, then your only good subarray is like the whole subarray, and that's only one. So the same frequency could have different numbers of good subarrays. So you have to go through it linearly, I think. Take the value, you increment the count. I guess here you can do like for a lot of it, maybe it's just not going to change much. So if the count of this value is like less than, let's go and just make sure I don't go infinite in this loop. If the count of this value is less than 1, well, let's say if it was less than 2, then you need to skip it. Else, if it's equal to 1, then equal, well, less than 2 is just equal to 1. If the count of the value is 1, then just keep on going. If the count of the value is 2, then pairs increase by 1, keep on going. And then else you do this stuff. So if it's 3, then maybe you can do another if statement there. I wonder if this is actually any good. I mean, caching the fine combinations should be pretty fast in terms of later calls. Pairs is greater than k. Okay. And then if you remove it from the left side, man, I don't know. This seems the same speed. There's, I don't know how much optimization this does. Like technically you only do this once for each right? Different, yeah. There's something I'm missing here. So the number of combinations, maybe I don't need to have 2 calls here. So what am I doing here? I'm increasing, I'm going to say 3 is added, 1 is added, 4 is added, 3 is added, the number of pairs is now 1, 2 is added, 2 is added, the number of pairs is now 2. So I stop there. And then I decrease the left side. And then I increase the right side until I get to 4. Yeah, so 4 is fine. Then I think I still need to track that. Is there a faster way than doing this calculation? Well, extend the right side of the window. Extend it out until I reach the second 2. Say that that plus the other one to all the way to the end works. And then I closed out the 3, extend out to the 4, and then I close out the 1. Close out the 1. Like the whole point of the window is the left side is the fixed marker for each loop. You see how far, how many subarrays start with that left side being at that spot. I wonder if this is just too slow, the line combination deal. So if you go from like 4 choose 2 to 5 choose 2, go to from 4 choose 2 to 5 choose 2. What is the formula there? 4 choose 2 to 5 choose 2. That'd be 4 factorial over 2 factorial 4 minus 2 factorial to 5 factorial over 2 factorial 3 factorial. So let's do the math here. So if I do the difference between them, 5 choose 2 minus 4 choose 2, this would be 5, or let's say n plus 1 factorial, or n plus 1 choose 2 minus n choose 2. So this is n plus 1 factorial divided by 2 factorial n minus 1 factorial. Is that right? 5, yeah, 5. No, 5 is n plus 1. N is being 4. 4 minus 1, yeah, okay. Minus n factorial, 2 factorial, n minus 2 factorial. And then, is there a common factor within that? So you could pull out 1/2 from both. That'll remove the 2 factorial from the denominators of both. So that'd be n plus 1 factorial divided by n minus 1 factorial minus n factorial over n minus 2 factorial. So that'd be 1/2 times n plus 1 over n minus 1 factorial. So that'd be n plus 1 times n minus n times n minus 1. If you cancel out the common factors in the fractions. So this would be 1/2. So you have an n factor, and you have an n plus 1 minus n minus 1 minus parentheses n minus 1. So it'd be 1/2 n times 2, the ends cancel, 1 minus 1 is 2. So n. Oh my god. So n? Doesn't seem right. 1 minus 1 is 2. Yeah, it's n. So but that doesn't right. 4 choose 2 is like 4 factorial 24 minus divide by 2 divided by 2, so that'd be 6. And then 5 choose 2 would be 5 factorial, which is 120 divided by 4 divided by 6. 120 divided by 6 is 20. I did something wrong here. Okay. N plus 1, choose 2. N plus 1 factorial divided by 2 factorial, n plus 1 minus 2 factorial. Simplifies to n minus 1 factorial. N factorial choose 2. Or n choose 2 is n factorial divided by 2 factorial. N minus 2 factorial. Seems fine. There's 1 divided by 2 in both, so you pull out the 1/2. That remains n plus 1 factorial over n minus 1 factorial. N minus 1 factorials cancels with n plus 1 times n. The other one, the n minus 2 factorial cancels with n times n plus 1. And then you can factor out n from both terms. So it'll be n plus 1 minus n minus 1. That should cancel. Alright, let's use numbers here. So 5 factorial over 2 factorial, 3 factorial, 4 factorial. Yeah, 5 choose 2 is 10. Oh my god, I did my math wrong. So, okay, 5 choose 2 is 10, 4 choose 2 is 6. So it is n. Okay. So I don't need to know this. I can just say that the number of new pairs, yeah, that makes sense. Like that new number, that new value of the count can combine with any of the previous values of the count. So, okay. So the number of pairs is going to increase by the previous count value. Pairs plus equals the count of the value before you increment it. Okay, and then here, after you decrement it, before or after you decrement it? After you decrement it is the subtraction. Okay. Counts, not count. Alright, so no need for this combination stuff. Okay, there we go. Alright, anything else? I mean, this is still kind of slow. I'm not sure. Like, you still need the dictionary to track the number of values, I believe. So the value, I guess you, like maybe you can simplify this. Value is the nums at right. the pairs increments by that value, and then the counts of that value increase, and then you change the right index. And then if the pairs is greater than k, then you go all the way to the end, then you take the left side, you decrement the left side value, you do pairs minus equals the left side value. Maybe you could go something like is enumerate for each left side index. Do you even need to know the index value? Yeah, so I think maybe you can say for left value in the actual thing. Left value in your nums array. So the value is just your left value. The left value is this. Pairs decrements by the count. You do need to know your right side index, but the left side index I don't think you care about. Huh, that made it worse. Well, whatever. Answer pairs. Okay. Good enough. Summary. This is sliding window technique. Extend for a particular left side of subarray. Extend out the right index until the number of pairs in between left and right index is at least k. Count all subarrays with at least that right side. Keep track of frequency of values. I used a default dictionary. And as you add new values to the window when extending right, increase the number of pairs, increase the count of pairs. And here math is each value will increase the pairs equal to the previous count of that value. So for example, third x will increase pairs by 2. After adjusting count, close left side window. Basically remove pairs from left. Move pairs due to left value removed from window. Alright, this is going to be a linear open technique. You go through all the rights each right side index is processed at most once. Same for left. And space complexity. This is O of. Did I actually create anything here? Yeah, so this is space for the mapping, and that's kind of like O of. I guess that could be almost O of n for mapping frequencies. No, technically, yeah, almost O of n. The number of values is bigger than the number. The range of values is bigger than the number of numbers, but then the number of numbers could be how many spots are within the mapping. Using default.